In topic number 4, we want to harken back to a theorem that we learned in Calculus 1 called the Squeeze Theorem, which I, of course, have a Desmos graph for you of. All right, so in Calculus 1, we learned that, hey, if you have a curve that is squeezed between two other curves, and those curves are both going to the same spot, they have the same limit at some particular value. So in this case, the absolute value of x, which is this blue one up here, has a limit of 0 as we approach 0. And then so does the negative absolute value of x, which is this red one down here. So then this wacky curve in between, which is x times the sine of 1 over x, which actually oscillates infinitely many times. It's a little trippy. It's like 2001: A Space Odyssey, which is a very old sci-fi movie. Go look it up. But it's a little trippy, but it's just oscillating infinitely many times. And as we get closer and closer to 0, it's oscillating faster and faster. So this is not a limit we can actually find per se analytically. However, we can find it with the squeeze theorem, because we can say, look, it's pinched between these two curves. It's rather obvious that the sine of 1 over x will never be larger than 1 or less than negative 1. And so as x shrinks, it will go to 0 because it's squeezed between these two curves, and both of these curves are going to 0. Therefore, the black curve in between is also going to 0. That is basically the squeeze theorem in a nutshell. Hopefully your Calculus 1 instructor said it to you, but just in case. And of course, it doesn't have to be 0. That one I just showed you is kind of a classic example. So if the limit of f of x and the limit of g of x are both L being this number right here, and this curve up here is going to L, which is f of x, or, oh, it looks like I switched h of x and, sorry about that, h of x and f of x, and then g of x is between. So sorry about that. I'll have to fix that. So this should be, oh no, it's correct, f of x and h of x. I was right. Sorry, this is h of x right here, right, this pink one. So h of x is going to that L value, and then f of x, which is this blue one down here, that's also going to L at this spot A. So if they're both going to L at A, then so must g of x. Then the limit as x goes to A of g of x must be L also, because it's squeezed between those two curves. See, g of x is right here, and it's squeezed between the pink one and the blue one at A. Okay, well, the same thing's true for sequences, right? Because if it's true for functions, which are continuous, then it's going to be true for sequences, which are discrete. So let me show you that. Now here we have it in Desmos, and I just made up a couple sequences so you could see the picture here. But I also wanted to show you that you don't have to do separate tables for the different sequences if they have the same entry values. I kind of haven't shown you this up to this point. So when you're making a table, here, let me just delete this piece so you can see how this works. So if I'm sitting here and I have this column already built, then I can just click over to the right, and then I can click over to the right again. There's another column in here, and then I can type, or in my case, copy and paste whatever I want, and I can make that turn into a different color. So there you can see, I can see all three pieces, and I can see in particular that that black sequence here is squeezed between the blue one and the red one. Since the blue one and the red one are going to 0, then so will the black one as well. And that's exactly what's being shown on this graph, right? So now, again, the particular graph I did was going to 0, but it doesn't have to go to 0. So this sequence, right here, this blue one with those blue dots, that's those dots. And the limit as n goes to infinity of c sub n is 0. You can, or excuse me, is L. It doesn't have to be 0. Sorry. There we go. Is L. And so is the limit of the pink dots, if you can see those, right? So those are these dots right here. Those dots are also going to L. And therefore, the sequence that's squeezed in between the two of them, which are the black dots, is also going to go to L. Right? It's getting sandwiched in between. Squeezed, in fact. That's why it's called the squeeze theorem. All right, so let's look at an example and try to prove it. There are occasional homework problems that do this as well. And you actually could see a little bit of what I was doing. Squeeze theorem is a common trick to use with a -1 to the n power. So if you have, like, so for example, this particular one, the black one I'm looking at, was -1. Technically it was actually over n1, but I thought that would be confusing because the dots, then half of them are black and it's a little harder to see. So I made it 2 times n1 just so you guys could see it more clearly, like there, for the illustration piece. But you can see the -1 to the n1, what's very common is to look at the negative and then look at the positive and then see if that function gets squeezed in between the two, which it does because it's equal to half of those points. So that's a pretty common trick to use, just a little FYI, right? To do the positive and the negative. So this is frequently used with alternating series, or alternating sequences. Oh my goodness. I mean, not all the time, but we'll just make a little note. Squeeze theorem can be helpful in a couple instances. Things that are when your a sub n is equal to -1 to the n over some function of n, right? I'm just going to write f of n. So it could be n, it could be n squared, things like that. So then you squeeze it between the negative and the positive, because -1 to the n is always between those negative and positive values. And then again, f of n could be anything. It could be n squared, n cubed, 3n, all sorts of stuff. Then another one that's common is when it's sine of n or something like that, or sine of some combination of n. It doesn't have to just be n. There could be sine of some, function of n inside, right? That's not really relevant, but it'll be sine. And that's because sine has to be limited between -1 and 1. So it'll be sine blah, blah, blah over some power of n, or, n cubed or something like that. And similarly cosine, right? Cosine of some function of n over another function of n, right? Because cosine and sine are both limited between -1 and 1, as is -1 to the n. So those are 3 very common ones where it can be helpful. Speaking of which, back to my example, I didn't get very far. If we look at that numerator, you can see that it's cosine of n. So squeeze theorem is helpful because of that. I didn't point to the numerator enough. So see that cosine of n? It's a red flag, right? When I see cosine, I'm like, I think I'm going to use the squeeze theorem, because cosine is kind of ugly, right? Cosine and sine in particular, those are the ones we use it a lot. We use it less for the -1 to the n part, but we really use it for cosine and sine because they're all sorts of values, right? It's a wave function, but we know it's limited by -1 and +1 to the n. Okay, so if I need to prove a couple things in order to use the squeeze theorem. So let's look back. The squeeze theorem says that I have to have sequences such that a sub n is less than or equal to b sub n, which is less than or equal to c sub n. Okay, so my first mission is going to be saying, hey, do I have sequences that are greater and less than this one? Well, yeah, sure, no problem. I can do that all day, right? A sub n is -1 over n squared plus 1. That will be less than or equal to b sub n, which is the cosine of n over n squared plus 1, which is less than or equal to c sub n, which is +1 over n squared plus 1. And the reason for that is because the cosine of any number is less than 1 and greater than -1. It has to be. All right, so part 1 is proved. We proved that we have 2 other sequences that squeeze this sequence, right? Well, we know it's between that sequence. We don't know if it squeezes yet. The squeezing comes from the limit. So we have this less than or equal to piece. Now we need the second component of the theorem, which is saying, all right, you have this sequence in between these two, but do those two squeeze together to L? Do they go to the same value, right? That's the pinching part. So we need to prove that. So let's find the limit as n goes to infinity of a sub n. That's the limit as n goes to infinity of -1 over n squared plus 1, which no duh, it's negative 1 over infinity squared plus 1, which last time I looked is negative 1 over infinity, which is 0. That is not indeterminate. We know what a constant over infinity is. It's 0. Similarly, we know the limit as n goes to infinity of c sub n is the limit as n goes to infinity of positive 1 over n squared plus 1, which is positive 1 over infinity squared plus 1, which is 1 over infinity, which again is 0. There's the pinching, right? There's the squeezing, right there. They are squeezing b sub n between them. They both go to 0, therefore this sequence has to go to 0 also. So that's part 3. Therefore, the limit as n goes to infinity of b sub n must be 0 also. So it's two components. You have to prove that you have a function that's a sequence function. So a sequence that's less than and a sequence that's greater than the sequence you're actually interested in for all relevant values of n. It doesn't really matter so much at the beginning. What matters is, as n goes to infinity. So if the first two are a little weird, that's not that big of a deal. However, that's not going to be a problem with cosine. And then I need to prove that those two, the lower, which is here, and the upper, which is right here, squeeze together. They're equal the same value, right? So limits are the same. I should have written that. That's the squeezing part. Since the limits are equal, therefore this other function, which was squeezed in between them, must also be 0. And again, you can see it on the graph. This is the actual graph of those sequences. And of course, I have it drawn in Desmos as well. I again did the large table rather than the 3 separate tables. And this time I put the lower one here, the squeezed one in the middle, and then the positive one over here. The order doesn't really make any difference. It's just for your own looking at it benefit. And you can see that that black sequence is squeezed in between the blue one and the red one. Therefore, all 3 of them are going to 0.